All right. So, as a follow-up to the class you had on deep learning, I'll be building on that to show you the practical aspects of how neural networks are trained. And because neural networks is a very broad aspect of AI, where you can experiment with different kinds of models, parameters, and techniques. I'll be taking you through a basic process of um, compiling, fitting the data, and visualizing the performance, and also be showing you how different parameters of the model development process affect the results of what you get. So a structure I'll be following would be importing the libraries as needed. So I could also explain as well the importance, the reason why we are using this library, and then would go on to the dataset importation process, which is something you are already conversant with. As well, the selecting the features, which is not something that is so deep. As you know, for deep learning, you don't really need much of feature engineering and feature selection. But then again, depending on the kind of data you use, you might have to separate your data set into test and train, for example, in the case where it is not separated already. Then from there, once our data is ready, we can move to create the model, compile, fit, and visualize. And it's going to be right because I'll be explaining the results we get, the parameters we are using, and the other options that could be used. Because I'll be using some specific parameters. I'll be explaining why they are used and the other options that could have been used aside them. So let's go. And also, if you have questions, I would appreciate it if you could drop them on the chat, or you could speak and ask as we are going. So I'm able to answer the questions as they come so you can follow along. And also, I also believe I had shared the notebooks yesterday. Was it this morning or yesterday? I shared the notebooks on Discord channel. So I shared two. I shared a workbook, which is what I'm showing you now. It doesn't have any code. We are going to be coding along. I also shared the complete notebook that has all the coding, right? So it's going to be a code along process where I'll be writing the code and explaining it as on the go. So that is that for now. Okay. So let's go back to the beginning. So basic architecture, that has been dealt with in the morning class, but for the essence of this lab, I'll just be going just a few minutes on it, as we're going to be building on this to develop our neural networks. So this is a simple structure of how a neural network is. In reality, you'll be having more than one hidden layer. This is just an example of a basic structure. As usual, you have the input nodes, you have the output nodes. And for the output node, it depends on how many, the kind of problem you are having. So for example, in a classification problem where you want to predict if someone has diabetes or not, that's like a yes or no, you'll be having two outputs nodes that's seen here. If in a multi-classification problem where you have 8 options, for example, to predict the and if an image is a specific digit, for example, 1, 2, or 3, that's like 10 options you have. You'll be having 10 output nodes here, basically. So with this, let's move into getting the data. So for this exam, we're going to be dealing with 2 examples. The first example, we're going to be trying to predict the model of a particular flower, which is the iris flower. Now, some of you might be conversant with the Iris Dataset, where we have 4 futures, and we are asked to predict the kind of flower it is based on the futures, which is the petal length, petal width, sepal length, sepal width. I'll be showing you all of these futures as we code along. So that's going to be our first example. And from there, I'm going to be changing different parameters and showing you how they impact model performance. So we'll be getting the data now. For the Iris dataset, it's available in the scikit-learn library. Now, the scikit-learn library has various kinds of data sets you can experiment on. So for this, we're going to be importing the scikit. We're going to be importing the data set from the scikit library first. So we're going to do from sklearn the data set import Iris. Okay, it should be load Iris. Then, because we're going to be saving this data we get into a pandas data frame, we're going to be importing pandas as well. Import pandas as PD. We have that already. So let's see what that gives us. So what I would want is I would want you guys to follow along as well, if possible, code along with me on your laptops. And if you run into any issues, do let me know so we can address it on the go, so you don't get stuck after a long time. So we have our importation. So from the load iris now, we can get the futures. So now the way the data sets work in scikit-learn, they're already separated into future and targets already. So for the futures data, we could say Iris data equals to load Iris. Then from there, we get the futures, and we're creating a data frame from the data we get from the load iris library. So pd dot data frame iris data dot data columns equals to iris dot data dot feature names. Now let me explain this line. So the way scikit-learn works, if you want to get the future values, it's usually stored as the name of the data itself dot data. That's how you access the future variables. Then the column names are usually stored as Iris data the data dot future names. So that's why I'm using the syntax, and the data frame, I'm assigning it into a name called features. Now, features could be any name. I just decided to use features because we're extracting the features of the Iris data sets. Then let's run this. Okay, we have an attribute error. So Iris data equals to Iris data future names. Okay, so this is the error. F should be in capital letter. So we run that. So now let's see what we have. Futures. So let's say we want to see 15 of them. So these are our future variables. So as I explained before, we have the sepal length, width, the petal length, and the petal width, all in centimeter. So now let's see how the target variable looks like. So we can say Iris data, the target. Okay. So if you see the target variables are already encoded use in zeros, ones, and so now I want to see the actual names, the names of this target instead of just saying the number. So we can say Iris data dot target names. We do this and we see setosa, versicolor, and virginica. Some of you are already conversant with these data sets, and the reason for choosing these data sets is it's easy to use to give explanations. So which is which is a goal to be achieved in this lab for you to have an understanding of how to develop your own neural network. So from there you can use more complex data sets and experiment. So we have our targets, we have our features already, and we also know the target names. So I have a question, guys. For these features, could you tell me so can you tell me if something about the numbers, the numerical values? Can you tell me something you've noticed about these values? All right, so Sarah said petal width and length are almost constant. Yeah, that's something. That's something. What about sepal length and sepal width? What do you think? So, like, what can you notice between sepal length and petal width, for example, like in terms of the values? Can you see anything like how different are the values? Yeah. So yes, that's it. They are not scaled properly. If you notice, that's very correct. You have the sepal lengths having ranges of 4 to 5, while you have petal width having ranges from 0 to 0.2. Right. So while in class, the instructor talked about deep learning not requiring much future engineering task, which is true. Also, it's also important that while training your deep learning model, you are looking at minimizing the time taken to train. So I could fit this, I could use this to train my net, I could use this data to train my network. But then again, I could also use a better data set that would give better and faster results. So in this case, we can move to normalize the data to ensure that all the values are within the same range. What that does, it makes it easier for the model to perform its own task of forward and backward propagation and trying to predict without worrying about how different the data values are. So the next thing we'll be doing is to normalize the features to ensure that they are all on the same scale. So I need to import the normalize module from sklearn. So from sklearn dot preprocessing import normalize. So we have that. Then so I'm going to be applying this normalize module on the features to ensure that they are properly scaled. So to do that, I could just say features equals to normalize and features. So now you see I'm using features. Okay. Sorry, there's a typo here. Normalize features. So I'm using features because this is the current features that we have, and the result of what we get, the result of normalization, I'm assigning it into features. So you don't need to worry about it having an error, an issue. It's just we're going to be getting a new result, and the result we're going to get will be the what we get after the normalization is done. So it's still saved as features. So you don't need to have like two different names. So when we run this, I would want to see what we have. Features. Let's say features.add. And okay, so now this is it. So when normalization occurs, it doesn't save it as a data frame anymore. It now becomes an ND array. So that's why I couldn't use features.ed, because it now says numpy ND array object does not have attribute ed. So now when we do this, we run this. So to be able to see what we have, I can say features. If I want to get the top the 20 values, for example, I can say this 20. So this means features starting from the beginning to the 20th value. So now we see that all the values are within 0 and 1. And if you see for here, we notice that the sepal length column are the highest amount of values, which is 5, 4, thereabout. And if you see here, now that we've normalized, it is still having the same, it's still having the highest amount of values, but still everything is within the range 0 to 1. So now that we've normalized, we can now split the data into test and train as you would normally do in traditional machine learning. So we say X train, X test, Y train, and Y test. Okay, so now I need to import the the train test split module, and we're going to be using sklearn for that as well. So I'm saying from sklearn dot preprocessing import train test split. So guys, I hope you see, I hope you're able to understand the importance of these modules. That's why I'm importing them on Go, so you can actually see how they work. If I had not imported this, it would definitely flag an error. So we can continue to use our train test split module as train test split. So now we can use our features. Now, for the train test split, if you're conversant with it or if you've used it in any project, it has an input of the train data, the test data, and the test data. So now we know our train data is features, but we didn't explicitly state our the target variables. So if you see from here, I'd already gotten a peek of what we have here. So I'm just going to be using this where I'm going to be getting the target variables from. So I could just paste it here. Then random states equals to 42. Now, I'm sure this would have gone over this before. The values here. Normally, if I'm using 42 and I want you to have the same result as I'm getting, you would need to use 42 as well. If I'm using 30, you would need to use 30 as well. If you want to get the same results as I am getting for the splits, not for the model training results. All right, so if no questions, I would move to do this. So there's an error here. Excellent processing. So what could be the error? Let's have a look at it for model selection. Okay, so it should have been, I think I made an error here. Should have been model selection. Let's try that and see if it solves anything. Okay, so we have our trained and test data already, right? So any questions up to this level? I guess none. That's nice. So now we'll be moving to encode the it's actually meant to be the target variables. So we're going to be encoding. So currently this is what we have for the target variables. So we're going to be encoding them to be able to feed them into the neural network. So for that, we can use a library from Keras. From Keras dot utils import so categorical. So now note that the current data we have is already in categorical, but we're going to be transforming it to one auth. So don't mind if this is still saying categorical. That's just the name of the library. And they could have chosen any name they wanted. So now that we have that, we're going to be encoding our target variables. So we'll do Y train and Y test. So that'll be Y train cat equals to categorical Y train, then Y test cat equals to categorical Y test. So let's run this. So now let me show you how the result looks like. Y. So now you see for each of the values, it's now one auth encoded as compared to the categorical encoding we had before. So now that we have that, we can move to model development, and I'm going back to this structure that we had. So in this process now, we need to define the input layer, the hidden nodes, and the output layer, which is what we're going to be doing now. So let's go back to the model development process. So defining the layers. Now, to start defining the layers, you definitely need to import some libraries, because we're going to be using the basic kind of model, which is the feed forward kind of model. So we're going to be importing the libraries for it, and also the layers we're going to be applying. We're going to be importing the libraries for that as well. So these are going to be gotten from TensorFlow. So starting from Keras.models import sequential. Okay, we have that already. Then from Keras the layers imports dense. Any chats? Okay, no chats. Then now we're going to start adding the layers one by one, but we have to define our model first. So we can use model equals to sequential. Now we've defined our model. The next step is to start adding the layers. We'll start with the input layer, then we can go ahead to say model.add. Now that's where dense comes in. Now, since it's an input layer, we have to specify the input dimensions. Now, for the input dimensions, it has to be the same as the amount of future columns that we have. And if you remember, we have 4 input futures. That's the petal length and width, then the sepal length and width, which makes it 4. So we'll be going ahead to define the first the unit, then the amount of input layers. So units equals to 64. Then input dimension equals to 4. Then remember we talked about activation function in class. Now, when specifying each layer, you need to specify the activation function that would be used to estimate the weights and the input processes that comes out of each perception as discussed in class. So now, there are different kinds of activation functions. We have the sigmoid, we have the softmax, we have ReLU, we have the step functions. And I would encourage you to practice with various kinds of activation functions and see, but from previous processes, from experience, you'll see that ReLU, the rectified linear units activation function, is commonly used when defining your layers, your dense layers, your input layers. Reason why it's being used is because of the non-linearity output it's able to deliver, which is able to capture the nuances of the data and the model structure as feed forward happens. So it's able to capture the non-linearity, which is why it's usually applied to each layer. So we'll be specifying the activation function now, which will be activation equals to ReLU, and that'll be that. We can access as input layer. And now we have our input. We could move to add a dense layer. So I'll be making the structure simple so you can grasp the basics of it. Then we can, in our second example, we'll be adding more layers and more a different kind of layer as well. I'll be explaining that, but for now, let's add just one dense layer. And I didn't talk about the unit. For this, you can use any amount. You can use 1, you can use 10 million. It depends on you really, but at the end of the day, you need to get the one that works best, the most optimal one. And I chose 64, not because it's a best number. I could have used 10, I could have used 50, I could have used 900, and I might still get the same results. So for different kinds of models, depending on the task you want to achieve, you'd have to find the number that fits for your specific needs. But for here, I'm using 64. So it's not written in stone, but if you are using online material, you could see that there's probably a particular pattern to using a particular number. You might see 256, you could see 64, you could see 32, you could see 16, those numbers. Well, so yeah, so let's add the second layer. Well, they'll add dense units equals to 64. Yeah, we don't need to specify any input layer because we've done that already. Then activation equals to ReLU as well. So that's been done. We're just adding one dense layer as our hidden layer. Then we'll move to add the output layer. Now, talking about output layer, the amount of neurons you would have, the amount of units you would have on your output layer should be equal to the amount of classes you're looking to predict for. So in a case where you have to predict if an image is a human or a horse, yeah, that means you're having 2 classes. Your output unit should be 2. In the case where you're predicting if a number is 1, 2, or 3, your output should be 3. In this case, we have 3 different kinds of flowers what to predict for. So the output number would be 3. Then we'll just do model.add dense units equals to 3. Then activation equals to softmax. So softmax, back to class. Softmax is able to be used for multi-classification systems. In the case where it was maybe you had to predict for 2 classes, maybe 0 or 1, you could have used sigmoid, right? But softmax works better for multi-class problems, so which is why I applied softmax here. So yeah, we'll be looking to run this now, but let me see if there are any questions. All right, no questions. So let's run this. All right, all done. So now if you're looking to look at the information about your model, the amount of parameters that it has, we could do that here. Let me cancel the output here and model.summary. And yeah, so this model.summary gives us details about our model, how many parameters each of the layers have. So you notice the parameter numbers are different for each layer, and to get the number of parameters, there's a formula for it, which is here. So to get number of parameters, you'd need to calculate the number of input features, add 1 to it, multiplied by the amount of neurons in the layer for each layer. So for layer 1, we add number of input features is 4, as we already declared here. Input dimension is 4 plus 1 times 64, which is the amount of units or neurons that are in layer 1. Now for layer 2, we're using 64 here because the output from the first layer serves as input to the second layer. So the number of input features for the second layer would be 64 as output from layer 1. That would be 64 plus 1 times the number of neurons in the second layer, which is 64, which we declared as 64 here. That's how we got 4,160. Then for layer 3, we do the same thing, 64, which is the output from layer 2 plus 1 times the amount of neurons in layer 3, which we have as 3, to get a total of 195. So now that we have an understanding of the model summary, we'll be moving now to compile the model. Now we've just declared the layers, we've initialized the layers, we've set our layers. For the model to work, we have to bind them all together, which we'll be doing now. So to compile the model, would say model.compile. Now we have to specify the loss that is going to be used to calculate the losses we have in our models. Back in class, you talked about different kinds of losses, categorical cross entropy, binary cross entropy, which are for categorical problems. But in the case where you're trying to solve a regression problem, you'll be using loss techniques like mean square error, mean absolute error, RMSE for regression problems. So now, yeah, it's a multi-class problem. So we're going to be applying the categorical cross entropy function. Someone has any questions? Okay. We're going to be applying the categorical cross entropy method. So we're going to specify the loss equals to categorical cross entropy, comma, optimizer. We're specifying this as Adam. 1 second, I'll give an explanation on that. Adam, then we can add the metrics. So now the metrics we're going to be using to evaluate the model evaluation. This is something that sounds very familiar. It's important to know how well your model is doing. So for a neural network, you specify it in the process of compiling. So evaluation Evaluation. Okay, I think this should be metrics. So the metrics for evaluation would be, for this case, we're looking at accuracy. In a regression problem, it would be something like mean absolute error, mean square error, depending. We could have used precision as well, since it is a classification problem. We could have used recall, we could have used F1, but you could try that on your own as well. But for the sake of this lab, let's use something everyone is familiar with, which is accuracy. So now back to the optimizer. The optimizer function explains the technique you are going to be using to improve the performance of your model. It also determines the learning rate, which we're going to look at very soon as well. But there are different kinds of optimizers based on what you're trying to achieve. In this case, we're using the Adam optimizer. Again, using the Adam optimizer, it has been seen to be to consistently work for a wide range of problems. In a more nuanced problem, in a different problem, you could use something else. It may work better than Adam. But in most cases, in a good number of cases, the Adam optimizer works well. You're also able to specify the learning rate if you want to change it. Yeah, but encourage you to try other kinds of optimizers. If you're working on your personal project and you're working on developing something, it's good to try others. They might outperform the conventional methods. So now that we have this, I've gone through the loss choices as well. So now that we have this, looking at everything, if it's all set, we can go ahead to compile. So compiling doesn't give any results. The results we'll be getting will be when we are fitting our data on the model that we've compiled already. So we've talked about the optimizer, loss functions, and the metrics. So now fitting the model, we can always assign the results to a variable. So we'll always be able to extract, for example, the accuracy, for example, the recall if we want, depending on what you set initially. So we'll say history equals to model dot fit. So now we're going to be specifying our data, our test and train data. So X train, which we have here. Then now this here, we're going to first be specifying the train data, which will be X train and Y train cat. Remember, we had encoded Y train to one auth data already. Then here we'll specify batch size. Batch size equals to 10. Now let me talk a bit on batch size. So imagine if you own a company that is making sandwiches, and say you want to produce the best sandwich in town and you are giving people to taste. So maybe you plan that for today, we're going to give 5 people to taste. For today, we're going to give 10 different people to taste, right? So if you look at it, you're producing different kind of sandwich. You're giving out different kinds of sample sandwiches for people to taste. That amount is what can also be explained as batch size. So the batch size determines how much training data you are feeding the model with at a go to train with, right? So if you use a very small data, it will take more time for the model to converge and get an optimal result. If you are feeding it too much data at a time, it might take time for you to understand the data very well and would lead to lesser prediction results. So it's important to know the right value to use, and you can only know the right value to use if you experiment. And a good way, a fast way to know the values for your hyperparameters is a method called Keras Tuner. Keras Tuner, it gives like the best parameters for you to use. But in that case, it is just feeding you with it. You're not experimenting on your own. You're not changing the values by yourself. So it gives you more understanding if you experiment with different values, if you can run for loops to for different values of batch size, for example, to to see the one that performs best, right? So yeah, we'll be using a batch size of 10, then epochs, let's say 50 now. Epochs talks about the time it takes for training to go on, right? So one epoch consists of a forward and backward movement of the data that is going through the model, right? So if you are moving data back and forth, back and forth, back and forth, you can do it 100 times, you can do it 10 times, you can do it 50 times, but in most cases, if you do it for a very short amount of time, the model has not spent enough time to understand the data. But if you do it too long, it may also take unnecessary training time. So there also has to be a balance between the amount you are using, right? Right, so now that we have this, we've set our epochs to 50, we're still going to set other parameters. Now the verbose, this talks about the output. Verbose equals to 1. So for verbose, there are different values for verbose, right? This is meant to be inside the brackets, sorry. Now, verbose talks about the way the output is displayed. So verbose usually has 3 different values, 0, 1, and 2, right? So 0 means when you're fitting your model, normally it's meant to give results. If you say 0, that means you don't want any results to be displayed. If you say 1, you want to see the rate at which it's usually going to show what do I call it now? Can I say a tracker that shows how long it has gone and how what remains for it to get completed. If you use 2, you say you still want the information to be there, but you don't want the tracker to be there. So we're going to be using 1 to see how far it is going, and we're going to see other parameters, which I'm going to explain. So we have set verbose. You could try it on your own as well. I encourage you highly to experiment on these parameters. I mean, this is how new models are gotten. You just like try on parameters, you see that okay, it works better than what has been existing for this kind of problem. That's how new solutions are created. So neural networks is something you keep experimenting with, you play with, and yeah, I hope you enjoy it. So now that we've specified that, we need to specify our validation data as well, right? So we already have our validation data means test data. So we'll say validation data equals to, now we have X tests and Y tests cat. So although there are other parameters you can also specify if you want to customize your model to have more options, you can always specify, but for this, you can always get a working model for this and get reasonable results. So we'll be going with this now. I'll just be going through it to see if everything looks good, right? Since we have no errors, I'll be looking to run now. So let's see what we have. Okay. So it's going through up to 50 and it's going very fast. So now, I'm going to be going back to the beginning to explain this. So like I talked about epochs, it usually outputs for each epoch, you get an accuracy, you get a loss, which is what has happened here. So for each epoch, we're getting values. And if you see there are 2 accuracies you can see on your screen now. You'd see the accuracy, the first one here, and you also see the validation accuracy. Same thing for the loss. So the first value, the first set of loss and accuracy are the accuracies and loss values it gets when using just the training data, when it's estimating just on the training data. But when it's exposed to the test data that we specified here, it also tries to predict against the test data and gets its set of validation accuracy and validation loss, right? So this is what we have here. We have the loss and accuracy. We have the validation loss and accuracy and validation accuracy. This validation loss and validation accuracies happen when it is testing with the validation data we provided here, which is X test and Y test cats. So for each epoch, it does this, it specifies the loss, the accuracy, and the time it takes to run all this as well. For data for models that are working on larger data, this might take a lot of time depending on how much data you have. This might take some good amount of minutes. So yeah, so it does this up until 50. So at epoch 50, we're having a validation accuracy of 0.9211 and a training accuracy of 0.9196, which is not bad. So there's a difference. There's not so much difference, which is what we usually aim for the training accuracy and validation accuracy to be the same, because it means that if the model is performing well on training data and is performing well as well on validation data, it means that the model is able to correctly predict new features it has not seen before. Right. But in the case where you have a validation accuracy that is significantly lower than training, that means there might be an issue of overfitting where the model is learning very much on the training data, but it cannot correctly predict on new data. So for this model, we would see that they are slightly the same. Even the validation accuracy is higher, a bit higher for the training accuracy, right? So that's it for the compile fits and fit process for neural networks. We've already explained these terms: epoch, verbals, training accuracy, validation accuracy. Then now, so for all these values, we can also decide to visualize them and see how they look like visually. And with that, I'll also be explaining some nuances as well, which you can see more visually. So now we're going to be plotting the results using Matplotlib. So I've already imported Matplotlib.pyplot as PLT. Now let's do a summary for the accuracy. So plotting for accuracy. So we've already imported as plt.plot. Then history. Remember, history is where we assigned all the results of the training. Back here, we map it to history. So you could as well have done model.fit without adding history to it. But if you want to be able to access the values easily, right, it's good to assign the results to a variable so you can always access what you want from the variable. So which is what we are going to do now. So we are going to be getting the accuracy values, history accuracy. We need just one. Okay, second one is out here. History accuracy. Then on the same plot, we're also going to be plotting the validation accuracy. This one is the training accuracy. Then history. So now we can say validation accuracy. It's already given here. right? Then we can add a title to it, plt.title, and say model accuracy. Then we can put the X and Y labels, plt.x label. What will be the X label now? The X label should be epochs. Epoch refers to the training time. Then plt.y label should be the actual accuracy values on the y-axis. Then we can add legends to it since we're plotting two values on the same, we're plotting two graphs on the same plot. So it's good to specify the legend as well. PLT the legend, say train test. So we're specifying the names of the legends and the location equals to, say, upper left. So it's at the upper left of your screen. Then finally we do plt.show to reveal the data. Then we'll do the same thing for the loss. So what I can just do is I'll copy all this, then modify it for the loss values. So plt.show, I'll say loss here. So there's a chat. If the accuracy is greater than the training accuracy, what does this mean? Okay, so for this, right, the validation accuracy could be greater than training accuracy in a case where the amount of validation data is significantly smaller than the test data. So for example, if you have like 100 values, 90 of it is for training and 10 of it is for testing. In that case, the chances of having more errors are higher. The chances of having errors are higher in the training data, while for the validation data, it might not even have since just 10 values. But in a case, it would also mean something that the model is not generalizing well to the data, is not generalizing well to the training data, meaning it's not taking like the properties, the nonlinear properties of the data, it's not capturing it well. That's what you call underfitting, like let me say the opposite of overfitting, right? So in that case, if it's significantly higher, if the validation accuracy is significantly higher than the training accuracy, you might need to check, you might need to probably update your model, for example, adding more neurons or reducing the batch size, for example, so it takes smaller batches of data, or for example, you can reduce the learning rate, right? So I hope that answers your question. All right, thank you. So let me minimize this. Model accuracy. So we're doing validation loss. Yeah, so we're still editing the plots just to be able to see what we have visually so you can appreciate it better. So here we have loss instead of accuracy train test. So this looks okay, hopefully no errors. So here we are. So for the accuracy, looking at the legends, we have two plots here. We have train, we have test, right? So if you notice at the beginning, the accuracy picks up from 0, it moves up. So like I explained before, as the epochs go, as the epochs increase, the model is understanding the data better and is able to make better accuracies, as we are saying. So it keeps going on and on. And if you notice at a particular point, it remains the same for both the training and test accuracy. It doesn't really change anymore. That's what I was also talking about, getting the optimal number of epochs. So you don't spend more time in training. There's a technique for that. It's called early stopping, knowing when to stop training the data, which you can experiment with as well. And if you also notice, in most of the cases, the validation accuracy is greater than the training accuracy. Yeah, but at some point, they level out together, right? So for different kinds of data sets, you might see different kinds of behaviors, which is an example of what we're seeing here. But one thing to note is so far the accuracy you're getting, so far there is no significant difference in the so if you notice, like I was saying, if the validation accuracy is not significantly lower or higher than the training accuracy, then most times you are good to go depending on the accuracy levels you want. And also this is just showing you how the process of training. So the accuracy values shouldn't bother you too much for now. Then the loss as well. So as the accuracy is increasing, the loss is reducing. As you can see, it goes from 1, it reduces drastically. How would you know the accuracy level? Okay, yeah. So in a case where you have to give people credit, like you have your bank, you have to design a credit system, right? And the credit system is going to be working based on different input parameters. For example, how long the person has stayed in the country where they're asking credit for example, or how much they have in their bank account, how many direct debits they have been setting, and how have they been able to pay up those direct debits. Has there be PNDs on their accounts before? So you're going to be using those parameters, right, to make an informed decision. In that case, you would want to have a high level of accuracy to ensure that you are giving the right people the right loans, right? Or in a cancer prediction case where if you make a mistake of wrongly predicting someone to have cancer, meanwhile they don't, there could be legal actions taken on you. In that case, you want your accuracy to be up to, I don't know, not in the healthcare field, but you'd want to have a very accurate of at least 98%, right? So depending on the problem you're solving, depending on the effects, the implications of wrong accuracies, what will happen if you wrongly predict something, your accuracy levels are depending on those factors. So that's how you'd know the kind of accuracy you want. But in real life situations, you really want very good accuracies. We expect, yeah. So now that we've trained our model and we've seen how it works, we can now decide to predict new values. We're going to be taking new values, like we're just going to be taking random values and see how the prediction process works. Right, so I'll be storing the new values in a dictionary. I'll call it new data equals to, so we're going to be using the same names as the future names here. These names, we're going to be using them as well, so it's easy to follow along. So we'll say sepal length, say this as 5.6. Then say sepal width because so let's say I'm just using random values. It may be different from what I have in the notebook, in the one I shared. Then hetal length, say 4.3. I'm just using random values. Hetal width. Petal width. What can we use as petal width? Say it was small in the features that we saw earlier. So we can use a small value like say 2.1. And now that we have this, then the same thing we did for the train data. We do it for the samples that we're going to predict now as well. That's to normalize it. So we'll say new data normalize equals to normalize new data. Then would also now use our model to predict. So say new predictions equals to model. We're calling our model now to predict on these new values. Predicts new data normalized. We have here. Now convert predictions to class labels. So now we'll do predicted labels and new data equals to new predictions dot max this equals to 1. Now, can anyone just guess? Just try to know the essence of this line, to just try to explain while we are passing our predictions into argmax. Okay, so all right, I'll answer this question after I run this code and we'll see what we have. Print predicted. Okay, so to get it. Yes, that's it, Usman. Brilliant answer. To get the label with the highest probability, right? Because the output from a neural network is usually in terms of probabilities, right? So for each of the label classes, it gives a probability, which I'm going to show you. So the one with the highest probability would be the answer. So for example, if you are traveling, for example, and they give that the probability that it's going to rain is 0.8, you most likely assume that it's going to rain because it's close to 1. So, but let's see it practically. Let's print predicted labels, new data, and see how it works. Okay, it's having a type error. All right, so there's something I didn't do, which is convert the dictionary to a pandas data frame, which is what I'm meant to have fed the normalized function with. So we're going to be converting to a pandas data frame now. I hope you are learning from these errors as well. So let's say new data equals to pd.data frame new data. So we can still use new data here. It doesn't change anything. So it doesn't change anything. We're just updating the new value, the value of new data. So let's see what we have here now. So now for this case, it predicts it as 1, but let me show you the raw value. You know, here we'll pick the one with the highest probability, and the one with the highest probability was 1. Now let me show you what new prediction looks like. New predictions. So if you see the results from the model that predicts argument give probabilities for each flower class. Right, so now you see the first one had a very low probability, 0.00. The second one had a higher one, the highest, the third one had 0.37. So this argmax just gave us picked the class with the highest probability. and outputted it for us. So yeah. So we're going to be looking at different what happens when we change different parameters. But I won't dwell too much on that because we have another example. So I'll take less time in the explanations. But one thing is when you're training your neural network, if you are going to be training different networks in the same notebook, to ensure that the results are independent of each other, it's always good to clear your sessions, to clear the previous session, the model training session, so it doesn't affect the results of the second model you're going to train. So for that, I'm going to be doing from Keras import backend as K. So now we can now do K as K. And now do K dot clear session, right? With a bracket. So now what this would do is it would clean up the model training processes that occurred in the first model that we trained. So doing that, we do that. So now we're going to be defining the model. We're going to be adding a second layer. So to make it faster, I can just come here and copy what I have. Yeah, I don't need to import again. Then I'll just add an extra layer to it. Yeah. Define the model with an extra layer. Then I'll just add an extra layer here. Model dot add. Then units equals to 64 version equals to relu. Same as one on top. I'm adding an extra layer. I'm going to run it, compile as well, get the compile code as well. So make it faster. For that, if you want to see the model information, you can also run model.summary to get an understanding of the model that you just defined. So model.compile, these parameters still remain the same. The only thing I'm doing is adding an extra layer. Then model.fit. So we have that here as well. Model.fit. So we're going to be seeing how, if the accuracy changes or not. So now what is the error? Sorry, I didn't compile. So compile fits. So let me see what we had in the previous training. We had the validation accuracy of 9737. Let's see if that changes. So yeah, it doesn't change. It doesn't change at all. Let's see if the loss changes. Well, apparently the loss reduced as well. So one thing you'll notice when you're dealing with neural networks is you may run the same thing now and run it in the evening again and get a different result. But it won't be a very significant result, right? It's the same way when someone asks you a question, the way you'd answer it will be different from if someone asked you the next day. So, and the idea of neural networks is it's trying to model the brain behavior. So yeah, we see that the accuracy doesn't really change. So for this kind of model, for this data, we can see that adding an extra layer with the current parameters that we have didn't improve the accuracy. For another kind of model, for another kind of data set, the accuracy could increase significantly if you added an extra layer or if you increase the amount of neurons. Yeah, and like I said, you can always play with these parameters and explore and, have fun with it. So let's see what will happen if we change the batch size, right? So now we're going to clear again. Dot clear session. We're clearing again. Yeah, so to make this easier to navigate for this output, okay, let's leave it so we'll be able to compare accuracies. So now I'll be going back since the adding extra layers didn't change it. I'm going to be using the initial amount of layers that we add. So I'll be removing this one out, removing it, compiling again. Compiling. Then for the fitting, something is going to change. We're going to change the batch size. So let's say we can use a batch size of 50 now. So we're going to change this to 50. All right, so let's run this. We'll run the k.clear session, defining the model again, compiling, then fitting it with the batch size of 50. Let's see what we get. Okay, so yeah, we see something different. We see that the validation accuracy has reduced when we increase the batch size to 50, right? So a correct suspicion would be that because we've increased the batch size, we're sending it the batch of data that the model is getting is too much for you to understand the nuances in the model. That's why it has a reduced validation accuracy. But for the training accuracy, it is higher a bit than the validation accuracy. Fair enough. So we can see how the batch size could have impacted it, but also in a different kind of scenario. Increasing the batch size might not reduce the validation accuracy. Perhaps it could even increase the accuracy depending on the kind of data you're handling, depending on what you have in your model already, depending on the parameters that are there already. So for example, I could come here and change the optimizer value. So the default optimizer value is usually 0.01. I could change it to 0.0001. And if I do that, then change the batch size to 50. For example, just for example, it could actually increase it. Because now, if I'm reducing the learning rate in the optimizer, that means it is taking more time to learn. It's learning at a smaller rate, but it's still having like higher amount of data per batch, right? So that could balance each other out, which are things you can experiment with. So for this case, it's at a reduced accuracy. So now let's play with the learning rate. Let's clear this session again. Any questions? And now this thing still doesn't come up. Okay, no questions. Carries a clear session. We'll clear again. We'll copy our model again. Define the model. Run this. So now, in this case, we've not been specifying the learning rates before. Sorry, please, for the new predictions above, none of the outputs. It's okay. Sorry, for the new predictions we did, none of the outputs is 1. So how did the argmax pick 1 and mine give me 2? Okay, so let's go back. Right, so I explained that the actual output is usually in terms of probability, right? So none of them would actually be 1. The one that is here is the label, the flower label that has the highest probability. It's not actually the value. It's actually like for example, if they say the house with the highest amount of stories, right? The house could have 10 stories, but it could be situated at like street 1. So it is the house at street 1 that will be referred to, not the amount of stories. So the one that is here is actually the value, label value, not the value of the prediction itself. I don't know if you understand that. Yetunde, you do? Okay, okay, okay. All right. Thank you. All right, so let's go. So yeah, I was saying, yeah, we didn't specify in the previous scenarios, we didn't specify a learning rate, but since we are changing it, the default learning rate is usually 0.01 for the Adam optimizer, right? So we'll be changing it now to 0.1 and seeing what happens because of that. So because of that, now we now have to like specify the optimizer that we are using to be able to change it. So we have to import the optimizer from keras.optimizers import Adam. Adam is the name of the optimizer we've been using. So from then we can now change the learning rate. So we can specify a variable called optimizer. We're specifying our own now. Optimizer equals to Adam into brackets learning rates equals to 0.1. So now we're specifying the learning rate. We're changing the default rate for the Adam optimizer. So we run this. Now we can now compile with the different optimizer that we have. So I'll just copy the compile function here. Compile. So now we're going to change this to the optimizer that we specified here. So instead of leaving it as Adam, we're going to put our own customized optimizer, which is same, it's still the same name. So you don't need to worry about it. Then from there, we can now fit, but let's compile first. Nothing has changed. The architecture has not changed, just the learning rates have changed. Run this, then let's fit. Now we'll notice that yeah, increasing the batch size reduces the accuracy. So we're going to put it as the initial batch size that we had before, which was 10, I think. So we're going to change the batch size to 10. We leave it as how it was before, and let's see what we get. Okay, so we have a lower accuracy now for training, and see now there's a significant difference. There's a significant difference in the training accuracy and validation accuracy. So let me explain what this is. When we increase the learning rate, that means that we're changing, you talked about gradient descent in class. That means we are changing the parameters to adjust to the result of the back propagation at a higher rate. So assume that, so let me use an example. In the case where you make, I'll use the sandwich example again, and you send sandwiches out for people to taste for free, and someone comes back to a good number of people, maybe like you sent out 7, and 5 people come back to say, this sandwich is too sweet. And let's say the sandwich has jam and butter in it. So you get the feedback that the sandwich is too sweet. That means the jam is probably too much. You can decide that, okay, let me reduce the jam by 2. The amount of jam I put, let me reduce it to half. Or you could decide that, let me reduce the amount to 1/4, like let me reduce it by 1/4. Or you could decide to reduce it by 1/8. So you're reducing it to half. That means just half that will be there. So let's say you reduce it to half now. Now, those are learning rates. You're adjusting it. You're adjusting the model training process, right? Little by little, right? But for the case of a sandwich, you're reducing it by half, you're reducing the jam by half. That means like that's going to make a very big difference, right? So you take it back, you reduce it by half and take it back, and people say it's not sweet at all, right? You're not getting good results because you're going to come back and keep reducing it. And if you keep reducing it in large quantities, you're not going to get like the real juice. So that's what is happening here, right? So Yeah, we reduced it, we increased the learning rate from 0.01 to 0.1. That means you're pushing the model to learn at higher rates. You're putting higher increments bit by bit, but you're putting it at the increments are too high for it. Right. So now that the increments are too high, right? After the iterations, it performs well on training accuracy. But when it's exposed to new data that it has not seen before, it doesn't perform as much. So in this case, now you can say the model is overfitting. And for this case, to resolve it, you can change the batch size and you can change the learning rate back to 0.01, the default, or you could even reduce it further to see the effect, or you could use regularization techniques. But if we had left it as default at 0.01, you won't need to probably add a regularization technique. But in the case where you leave it as default, you change it and the accuracy doesn't increase, you might have to add regularization techniques, which because of time we won't be covering in this lab, but it's the same steps of regularization in traditional machine learning. You just need to add the L1 and L2 parameters to it when you're training the model. So that's it for this one. So let's see how increasing the number of epochs will change anything. All right, okay, that's clear. Backend. I hope that's the correct code. Okay, so what is wrong here? What am I missing? Clear session. Bad. So let's run this. So the difference between what we're going to do now and what we have before is just increasing the number of epochs. So again, I'm copying this. Pasting here. So what increasing the number of epochs is like you just have more time to train. So all the back and forth that that's going to be happening in the model, it has more time to do, it has more time to learn. So normally, if the epochs were not enough before, increasing the amount of epochs should increase the accuracy. Now, we don't need to specify an optimizer again because we're using the default. So we don't need to specify. So this will be out. We're just going to compile normally using the Adam optimizer. Compile. So I'm changing this back to Adam. Then I'm going to copy the fit code and change the epochs to 100. So instead of 50 now, 100. So run this, run this, run this, and we have this. So let's see what happens changing it to 100. So look at the process now. If you notice, let's go to where it was 50. At epoch 50, we got 9737, which is the highest accuracy we've gotten so far. But see, as we keep going down, it keeps staying at 9737, then it keeps reducing to 9474. It keeps oscillating between 937, 9737, 9474, like that. Then it ends with an accuracy of 9474. While the training accuracy is still way high, it's a bit significantly higher than the validation accuracy. Suspicious of overfitting, but yeah, so for this one, let's visualize it. Let's see how a longer amount of epochs changes the visuals, just for you to get a feel of how using extensive number of epochs would look like. So sorry, I'm doing a lot of copy and paste here just to make things faster as time is going. I think we have 15 minutes more. So I'll drop this. So after this, I'll just run through the second example, which is interesting as well. So I don't need to import this. We have it imported already. So let's run this. So this is it. We have it coming from 0, stalling at 9, 7, alternating, 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 alternating. If you notice at some point here, the test accuracy was higher, was higher, was higher. Then at some point, the training accuracy was able to pick up as well and be higher at the end. Right. So these are the things these are the nuances you are going to see in the process of model training. Hope there are no questions. So now we're going to go into a different example, right? So for the first example, we got our data from scikit-learn. Now we're going to be using a different library to get our data. Again, you don't need to download from any site or from GitHub. It's going to be accessible from the code. So yeah, we're going to be dealing with a fashion data set. This is an image classification data set, right? The task here is to predict fashion items, right? It's going to predict sandals, sweaters, sneakers, bags, and we're going to be seeing how that works. So first thing is we're going to be importing the data from TensorFlow. Then for this one, the training and test data is already mapped, so we won't have to be splitting into test and train anymore. So I'm going to be showing you how that is done as well. So from the Keras library, we're going to be importing the data set is Keras.dataset, same way we did for scikit-learn, import fashion MNIST. Right, then from there we map the data. It's already mapped already. It's already like separated into test and train, but we just want to like assign them into variables. So we're able to use those variables in our model training. So train image. You can call this anything you like, so far you're consistent with it. Test images. Okay, should be train images and train labels, comma, test images, comma, test, and train images, train labels. Okay, this should be test labels, and this should be train labels. Train labels, test images, equals to fashion and is dot load data. So we're just mapping the train and test. So what happens when we run this? So it's downloading from the TensorFlow datasets. It's running. Right, it's all done. Then this is just a diagram, a write-up of the various input, the labels that the 0, 1, 2 that maps to each. So for you now, when we're training a label, the output would have 8 units because it would have 10 units since we're having 10 labels here. So just to show you the nature of the data, we're going to just be printing the shape of the train and test data. So print train images dot shape, then print test images dot shape. Then we go down. We do the same thing for the labels. Print train labels the shape, then print test labels the shape. Then just the length of the data, print len train labels, then test labels as well. Print, length, test labels. So we have this. Let's see what we have. So as seen here, for the train images, we have 6,000 of them. For the test, we have 1,000, and there are these dimensions because they are images, right? Then for the train labels, 6,000, tests 1,000, then just the length, right? So after that, we would want to get so for this one, I think we can skip this one since it has already shown you. I wanted to show you how to like get the count for each of the labels, but we can do that as well. So for each one, we can say class labels equals to class names label for label in train labels. Then create a data frame labeled equals to PD the data frame. Then we just want to get the count of each label. Count train labels, comma, class train labels. Then just group by class, class counts equals to labeled the group by class dot count. Then we'll just visualize it. Class counts. Let's see. Hopefully no errors. There's an invalid syntax. Where is the syntax error? Train labels. Class train labels count PD dot data frame. What's the error? It's saying count class. So what could be the error? Please bear with me. Okay, this is meant to be as a dictionary. So yeah, it's meant to convert the dictionary that we've created in here to a data frame. That's the error. So now we have this. It shouldn't have shown it as numbers. It's meant to show it as the actual names of classes. But I hope you get the gist of what I'm trying to do. Right. So it's something we can fix, but just to ensure I cover all in time, we can just move to something else so I can cover everything for you. So the next thing is I'm just going to be showing you how to use plotting. The previous one we used Matplotlib to show our visuals. So Plotly is a kind of visualization that even provides more customizations than Matplotlib. So I'll be using Plotly for this one. So I have to import the Plotly library first. Plotly.express as px. Then we're going to be displaying one of the images because to px.im show. And one of the train images, the first one, train images as the first one. Then title. What? Sorry. Lovely. The express title equals to first. image in train data. All right, so we can add the color, big, the updates, layout. I'm sure for most of us, Plotly is in your kind of visual, but it's something you should really look into. It can create really beautiful visuals for you. Color axis, color bar. So title equals to color scale. So this should be in caps. Should be in caps. Then show would be feed the show. So let's see what we get there. Okay. It's meant to have shown a picture, but don't know why it's showing numbers instead. 1 second. Title pix, my image train, color axis, depth. All right, let's try this again. Okay. Then from here, import Plotly expresses px, px.aim show train images, title, data update layout. Okay, there's the error. Yeah, so the error was I didn't add a bracket to the fig.show. Okay, yeah, I have the chat. Yeah, figures. Thank you. Thanks. So yeah, so we have this. This looks like a shoe. So now we're just going to want to encode our test and train outputs. So it's the normal process, train labels equals to pattern, like we did in the first example. Train labels. Then same thing for test. Test labels equals to 2 on top categorical. Test labels. So we encode this, then review the new label shapes. Just it should be the same thing. Let's just see for train labels, the shape. Yeah, same thing as that. Then we'll normalize as well. Same thing we did at the beginning. We are going to normalize the input, the train images, right? Because we'll be dividing by 255 because of the way pictures are, each picture usually consists of a pixel that has ranges from 0 to 255. So we're going to be normalizing everything to be between 0 and 1, which is all we're going to be doing. So we're going to be doing for the train and test. Train images equals to train images divided by 255.0. Same thing for test. So we do that, run that, then start with model training, right? So like I said before, this one is going to be a bit different from the first example because we're going to be adding some actually 3 different kind of layers that we didn't add in the first one. So I'll be explaining what these layers would be doing. So the first one is to flatten. So now if you notice, we're dealing with picture data, right? So now these images would have different values and different different characteristics. So what flatten does is it ensures that all of them are in the same shape and arrangements, which is what the flatten does, right? So we're going to be importing the flatten module, which is from Keras. dot layers import flatten. Then second one is from Keras the layers import batch normalization. Now, okay, batch normalization, you might think we already normalize the input images, but the thing is, for each layer, the output is different for each layer. So, okay, I'll explain to you when I start arranging the layers, but the third one will be the dropout layer. I'll also be explaining that from Keras the layers import dropout. Right, so I'll start defining the layers and I'll be explaining what each of the layers is doing. So define it like we usually do. Model equals to sequential. Then we're adding the input layer, model.add. So the first thing we're adding a flattened layer. You could try without adding it. It's not something you need to add. It's not a given. You could test it without adding it, right? Input shape equals to 28 by 28, right? Then we're going to add in a normalization layer, model dot add batch normalization, right? Right. So for the reason why we're adding the batch normalization before creating the second layer is to ensure that the output from this input layer, right, it's in a way that is easy to understand for the second layer, since it is images and they are heavy. So it's best if you add things that can make the model training process easier. That's why we're adding the normalize, just to make sure that the input to the next layer is it's informed and it's easy to digest for the new layer. So from there we can add the second layer, which is now the hidden layer. Model.add lens. Now for this one, you could decide to use 150. You could try it with other numbers as well. Activation equals to relu. Add that, then we add another batch normalization. Right, so how many layers do we have now? We have 2 layers. We have 1, 2. These batch normalizations are just for optimization, so we could decide not to count them as part of the layers that we have. But in the model summary, we're going to see how it looks like. So then we'll go add another layer, model.add. Then another 150, for example. 150 activation equals to relu. Okay, then for me, I could decide to add a dropout layer, right? So model.add dropouts. Now, for this dropout layer, what dropout means, it's a way of performing regularization as well. What dropout is doing is, for each of the layers, right? For the layer before it is deactivating some of the neurons. If you notice, the dropout layer is after this dense layer. So it's deactivating some of the neurons in the dense layer to ensure that the data does not become too dependent on all the neurons. It's not too dependent on the same kind of neuron. So it deactivates some parts at a particular rate. If I had used 0.5 here, that means it deactivates half and leaves half. Then for the second iteration, it will deactivate the other half. But if I'm doing 0.2, that means I'm deactivating at a rate of 20%, deactivating 20% of the neurons, then leaving the rest activated. Then for the next iteration, I deactivate another part and leave the other part. So the model is able to survive without having to depend on any of the neurons in the model. That's the essence of dropout. So we could add another dense layer. Model.add dense 150 activation equals to relu, right? And how many dense layers do we have now? We have 3. Then we could add another dropout. So if you notice now, this is like you're building a house. You can create it in any way you like. And yeah, so we add another dropout here. Then let's just add another dense layer. And for me, I'll just copy, paste, then add a batch normalization layer again before creating the output layer. Like I said, the output layer will depend, the amount of neurons will depend on how many labels you have to predict. So this would be dense. We have 10, so we are doing 10, comma, activation equals to softmax. And you remember the reason why we're using softmax. So we have this. I could decide to add another normalization here, but let's see how this works. And let's see if there are any problems. There's a name error, flatten is not defined. I didn't run this. So now that I've run this, and just go through this and see. Okay. Normalization, yeah. So let's run this and see what we have. Now that we've defined, we can compile the model now. So the same way we compiled in the first one is the same way we're going to compile in the second one using the Adam optimizer. So I'm just going to get the code so we don't have to type it again. It looks like it would have been faster if I typed it. So compile. Let's check that the parameters are correct. Add categorical cross entropy. Then now we can move to fit the model. Right. So now the fits, it will be different because our train and test data are different. History equals to model dot fit train images as input, train labels as target data, batch size equals to 30. Now we're going to set, because this data is very heavy, if I set it to like 50 or 100, as I did in the first example, it will take a long time to run. So I'll use verbose equals to 2 here for you to see how it looks. Then validation data equals to test images and test labels. Let's see what we have. Okay, type error, epoch, meant to be epochs. Let's see. So you can see how long this one is taking to run. We've not even done one epoch yet. So because it's image and it's very heavy, it's heavy inside. So this is not about neural networks. Sometimes it might take time, sometimes it might be very fast, depending on how big your model is and how big your data is. So if you notice, we're using verbose equals to 2 here. That's why we're not seeing the tracker of how long it's taking compared to what we had in the first one. Let me show you. In this one, we had some that was running like this. So if I put verbose equals to 1 for this second example, because it is slow, you'd be able to see the tracker of how long it's taking to complete, how long remaining for it to complete. But I use verbose equals to 2 years, so that is not showing. So we'll just wait this out. Try and see if... Okay, no questions. Oh, well, I spent more than... So while that is on, I could just type this model.summary just for it to get ready. Then here again, we're going to be using Plotly, and this one you might not understand it immediately. You might have to look at it a second time because Plotly is not something that is frequently used, but I'll try my best to explain it. And that'll be all for today. Thanks for staying with me. So we're at Epoch 8 now. We have 7 more to go. But while that is running, let me create the code for the visuals. So the way it's the visualization process for Plotly, if you are making 2 visuals at the same time, you have to create them in form of subplots, right? So I've already imported the libraries. Goal is to make the scatter diagram. Subplot is to ensure that you can create 2 plots on the same line, right? So I'll be creating the subplots now. So phi equals to make subplot row equals to 1, columns equals to 2. So this means that we're having 2 plots side by side. That means we're having 2 columns. As an example, see the outputs, this column 1, column 2, but they're all on the same row, and we're having just 2 diagrams. So it's going to be row 1 and columns equals to 2. Then set the titles, subplots titles equals to model accuracy and model loss. I have a chart. Okay, that's for the attendance, model loss. Then we are going to be adding each of the diagrams now. So we'll start with the accuracy. So this is almost done. So we'll start the accuracy. We're going to be adding it as a trace. Add trace. Then we're going to be creating it. And for plot, the syntax to be, for a line plot, it would be a scatter method to call. Go.scatter. Then the x would be the length of the accuracy, the length of the accuracy values, which would be the same thing as the length, the epoch, the amount of epochs. Okay, we see that our model has completed, it has run completely, and we get an accuracy, a validation accuracy of 0.88, a training accuracy of 0.9. So we can see that this model would benefit well from regularization. And perhaps if we added an extra layer here, it could also reduce the difference between the validation accuracy and the training accuracy, which is something you should experiment on. But let's finish these visuals and talk about it, and that will be all for this class. It's past time already. Then fig.add trace, I was going to write this one, go.scatter. So the x-axis would be the length of epochs, which you could still write as range of the length of the accuracies, range 1, length of the history, accuracy. then plus 1, comma, y equals to history, the history accuracy, then the mode equals to line because it is a line plot and the syntax is different for plotly. Mode equals to lines and the name equals to train accuracy. So let me see that everything is correct here. Just list my range 1 length history accuracy plus 1 y equals to history accuracy mod equals to length then equals to training accuracy, then comma, then the rows that they are going to be located on, row equals to, okay, I could bring this down to make it visible. You say row equals to 1, column equals to 1, saying that the first trace will be located in row 1 and in column 1. So why is it flagging this? All right, so I might as well put this on the same line and let's see if it changes anything. So we need to check. So there's meant to be a bracket here, a comma here, and I bring this down. There's meant to be a bracket here. So that looks okay. So we add the same thing for the test accuracy. The names are just going to be different. So I'll just be copying and pasting. Length, test accuracy. This one now will be validation accuracy. Val accuracy. Val accuracy. Validation accuracy. So the same, that going to be in the same plot. So it should still be row 1, column 1. So for the loss, it will be column 2. That's the thing that's what is going to change. So let's copy this and add for the loss function. So here it's going to be loss, and it's going to be loss here as well. Loss. Yeah, it's coming training loss. And then do the same thing for the validation loss. Validation loss. Validation loss. And yet to change here. Loss. So yeah, we're going to change it to column 2 because it's going to be beside it. So it's going to be in the second column. Column 2. Then just update the subplot properties. This is not so necessary. You could check it out in the notebook, but it's just a way to customize it. It's not something you need to do. Then we'll just the title, we can update the title, say fig dot update layout, update layout, title, text equals to model performance. Then you can increase the height if you want to make it bigger or smaller, 500. Width equals to 1000 to make it wider so it can accommodate the two graphs. Then you can change the template as well. It's usually white by default, but if you want to change to black, you could use the plotly dark option. But let's see how it is. Fig.show, and hopefully there are no errors. Okay, error. Type error. Where is this? Rows equals to 1 and 2. So what is the error? Loss, training loss. 5, 1:1. So, okay, it's yeah. So what is the error? I'm trying to look and see what it could be. Make subplot rows. Okay, this is the error. Meant to be rows, ROWS. Hopefully that solves it. It's still highlighting. So what could be it? Subplot titles. Meant to be
subplot.
Yeah. Fig.show. Hopefully it runs now. Yeah, looks like it's going to run. So if we had used plotly dark, let's say template because of plotly dark. Let's see how that looks. I usually prefer the dark option. Okay, what is it? Plotly dark is not defined. It's meant to be. Mark here, perhaps. Okay, so this is the dark version. So it's trying to show the visuals for the accuracy results as well. So we had concluded before that it was overfitting, which is something the graph has also displayed as the train accuracy trumps the test accuracy, and the training loss at some point it is higher. Then as the training increases, the epochs increase, the training loss goes way lower than the validation loss, which is higher. So this is different from what we had in the first example. So like I said, different models would give different results based on the parameters you are using and your architecture. It's something worth playing around with and experimenting with. But for now, this should be the end for this lab and your last lab for cohort 8. Thank you for staying this far. Thank you for listening to me as well.